So good morning, everyone. So we continue our Oscar test. So Oscar, you get my congratulations with your 50th birthday. That's very nice. So Oscar for us is the Pink Midas of Iberian Peninsula, Rex Midas Iberius. For everything he touched, math, organization, music turned out into gold. So congratulations to your 60th birthday. And this is the best I could give you as a present. One of my best friends, collaborator, great mathematician, communitarian, a friend of mine for many, many years, Tony Pantev.
Thank you. It's really great to be here to celebrate Oscar's birthday and to speak. I try to remember when I met Oscar for the first time. I think it was in '95 at MIT, but
much earlier at the MSRI.
Really?
In 92.
Maybe in '92, yeah. Okay. Well, but anyway, so we spent quite some time together at MIT and at MSRI. And the first time I came to Spain, actually, was because Oscar invited me, went to a conference in Toledo. It was an amazing conference. It's been a long time and a wild ride. And we've talked about math for years and exchanged ideas and used each other's works in many different ways. So congratulations, Oscar. And I'm going to try to give a talk about the topology of wild character varieties. I've tried to give it once before and couldn't fit it in 50 minutes. So probably I won't be able to fit it in 50 minutes today either. But we'll go some way. It says geometry and topology, and I was originally planning to talk a little bit about the Poisson geometry of wild character varieties too, which feeds into the topology, but that would have made the talk really much longer. So I'm going to say very little about the geometry. It's mostly going to be about the topology. Okay, so this is. Okay. This is based on a series of joint papers I wrote with Diaconescu and Dunaghi, and with Chuang, and then with Diaconescu and Chuang and Dunaghi and Nawata. It's about this string dualities approach to understanding or extracting topological invariants from wild character varieties. So I'll briefly review just so that we'll set the stage, even though in this audience everybody knows what we're talking about. The wild character varieties. We'll talk about the question of understanding, packaging the topological information and understanding that package through the weighted Poincare polynomial. And then we'll try to explain to you this string duality approach, which essentially takes three conjectures, one from mathematics and one from gauge theory and one from string theory, puts them together and uses those conjectures to actually compute weighted Poincare polynomials of wild character varieties. And then you can think about, once you have a formula conjectural produced by this strategy, you can think about how to try and prove it. And sometimes you can prove it by localization or by some other method. the whole story will be about creating this massive dictionary that translates one enumerative problem into another one that you can actually solve. And in this particular instance, so there are various ways to convert the weighted Poincare polynomials of wild character varieties or tame character varieties or unramified character varieties into something different that's computable. And in this particular instance, it will be covert knot invariance, covert quantum knot invariance that one can compute by some physics process. So it will eventually just use some formulas of Shakirov and Aganachik. Okay, but so let me talk about wild character varieties. So we know what they are, right? Character varieties are just modular spaces of matrices, special collections of matrices. And what they really are, they're like the Bethe incarnation of moduli of flat connections on Riemann surfaces. So they parameterize monodromy data for meromorphic systems of linear ODEs on Riemann surfaces. And we know they come in three basic flavors: unramified, tamely ramified, and wildly ramified. So the unramified ones are monodromy data, parameterized monodromy data for connections with no poles. The ramified, tamely ramified ones require the connections to have poles, but logarithmic ones, first order, and the wild ones allow connections with arbitrary poles of arbitrary orders. And yeah, so in the tame case, you know, right, we write the basis of loops on the Riemann surface, the monodromy of a flat connection along each loop. So fix a flat connection, the monodromy is a matrix. Say the flat connection is on a vector bundle for simplicity. And then you get 2G matrices and you want one relation, which is the relation in the presentation of the fundamental group that the product of the commutators is 1. So you look at these 2G tuples of matrices, modular conjugation, and that's the unramified character variety. In the tamely ramified case, there are punctures on the Riemann surface. So you have some extra collection of loops that go around the punctures, these C guys. And then the relation in the fundamental group changes. So you have the commutators around the standard loops, and then you need to multiply by those extra loops. And again, you want to assign a matrix to each of them and look at that product, and that's the character variety. Now, the wild one is trickier because, again, you're dealing with punctures, but if you want to codify the monodromy data of a connection with higher order poles into a collection of matrices, you need to do some extra choices because you need to worry about asymptotics of asymptotic behavior of solution, flat solutions of your flat sections of your connection. Okay, so let me try to explain that quickly. So there is a data that you need to fix. This Gothic X is going to be a smooth projective curve, the compact one. We'll have a bunch of points that we're fixing, distinct ones, and I'm gonna oscillate between vector bundles and principal bundles, but mostly talk about vector bundles. But say G is a reductive group with a Lie algebra small g, and so you need to fix that. That's the background of your character variety moduli problem. And you also need to fix some local invariants for your connections near the punctures. So these are going to be the punctures where the poles of the connections are prescribed. We'll be looking at principal G bundles and connections which are homomorphic outside of the points and have some meromorphic behavior near each puncture. So in order to control your moduli problem, to make it manageable and distinguish it from nearby similar moduli problems, you need to fix the local behavior of the connection near the punctures. So these are these irregular types. I'm calling them Q1 through QK. So it's one piece of data for each puncture. And there is also another piece of data that you need to fix, which is a conjugacy class in the group, which is the conjugacy class of the formal monodromy of your connection near the puncture, so I'm gonna try to say what each of those guys are. So we want to study monodromies of flat connections on principal G bundles. The connections are meromorphic. The poles are pinned down to be at the points of D. These QIs are the polar parts of your connection at each point xi. The formal monodromy, once you fix the polar part of your connection, so you're looking at a local connection on a disk with a given Laurent tail of the connection matrix, then there is one monodromy piece of data, which for these classification purposes is not really the monodromy of the original connection, but what you have to do is you have to convert your connection with higher order pole to a connection with first order pole by doing a formal gauge transformation. So we can always do that. We can always take a formal gauge transformation near the puncture and reduce the order of the pole to 1, and then take the monodromy of that connection. So that's the conjugacy class you need to fix. And so these irregular types, they're given by, as I said, Laurent polynomials with coefficients in principle in the Lie algebra. But since we're looking at the part which is of order, has polar part which has order of the pole 2 or higher, these coefficients actually can be conjugated to be in the Cartan. And so yeah, so you require your connection. So you fix this Laurent polynomial with negative degrees only. And you require your connection locally to look like up to gauge transformation D plus DQ. So as you notice, because we're taking the derivative of this, in this form there is no first order pole. So this only fixes the higher order pole information. And yeah, I already said that, but if you do a Puiseux gauge transformation, the polar part of degree -2 can be always made diagonal. And which surprisingly is not an easy statement. It's one of the core statements in the classifications of irregular flat connections on a disk. For Higgs bundles, this is a trivial statement because it's just a Jordan canonical form statement. But for flat connections, it requires some thought. And okay, so what you do then, you take your punctured Riemann surface and you make it a Riemann surface with boundary, which just means, okay, you take the real blow up of the Riemann surface at each point, replace the point by a nearby circle, and then so then what you need to do, so this circle is, of course, it parameterizes the rays, the real oriented directions emanating from the point, and you get a surface with boundary. And then what you need to do is you need to take the irregular type and convert it to some topological data And if you study asymptotics of solutions of your model flat connection on the disk given by the irregular type, you get stock sectors. And that these stock sectors actually decorate this circle, this boundary circle, with additional data. So you get these reductive subgroups in G, which are the centralizers of the QIs, the coefficients of the power part of the connection. And then you get a finite set of special points on the boundary circle, which are what classically is called the anti-Stokes directions. These are the directions where the convergent solutions to your differential equation in a sector stop being convergent, and you need to resum in order to get a different solution. And then for each of those points, you actually get a unipotent subgroup in G, which is normalized by the subgroups Li. So you can, so Phil Bolowski came up with this way to record this data in a topologically meaningful way. You can get a new punctured surface X twiddle by taking the original surface X minus the points, and then puncturing it further once near each singular direction. So so what you do is you take, so if you think about the original compact surface as being this hole here is the puncture, which we promoted into a boundary circle, which is this little inner disk. And then we can inner circle, the black one, and then you glue a little annulus to it, and then you puncture, you add additional punctures on the boundary circle near each Stokes direction. So you get this new surface X plus with the gluing, and once you puncture it, you get this X twiddle. And now you can look at the covariantly constant sections, analytic covariantly constant sections of your flat direction that gives you a locally constant of your flat connection, that gives you a locally constant shift on X twiddle. And it's a special locally constant shift. So it's what's called the Stokes G local system of irregular type Q. It depends on the irregular type because we are looking at connections of that particular type. So yeah, so these are the conditions that you get. It's a principal G bundle on X twiddle, and it admits a reduction of the structure group on this annulus, or in fact on some finite cyclic cover of that annulus, a reduction of the structure group to the group Li, so that the local monodromy near each of these new punctures is in this unipotent group that the asymptotics gave us. And that's for any choice of a base point in the disk. So this is the topological data. The topological data is a locally constant shift with that particular property. And so you can think about it as a local system, but because of these conditions, it's more natural to think about it as a constructible shift, because the conditions are specified on a stratification given by these disks. Unconditionally, it's a local system, but unconditionally, it doesn't carry the information you need in order to encode the flat connection. You need to put those conditions, and then it's really a constructible shift with those conditions. Okay, but so these Stokes geolocal systems are are the Betty version of the Betty incarnation of the flat connections of irregular type Q. In fact, the irregular Riemann-Hilbert correspondence in this form, it was proved by Phil, can be formulated by saying that the category of flat meromorphic G bundles of irregular type Q is equivalent to the category of Stokes G local systems of irregular type Q on XD. And so the wild character varieties are going to be the moduli spaces of Stokes G local systems. So here is the type of question you want to study. You fix a group G, you fix an irregular type, fix conjugacy classes in each of these reductive subgroups that are described by the irregular type, and you want to look at the coarse moduli space, say, Stokes G local systems of irregular type Q, or you can restrict it. You can look at the coarse moduli space of Stokes G local systems of irregular type Q, for which the local formal monodromy are in the given conjugacy classes. So they're both interesting. So this one is a slice of this one, and in fact, this one is a Poisson variety, and this one is a symplectic leaf. If they're smooth, and if they're not smooth, then you have to resolve them somehow, and then it's still correct. Okay, so I want to talk about the topology of these guys, and let me just, I mean, you've probably all seen this question in a much deeper context, but let me just give you somehow the baby version of what we're trying to do. Say that you have a finite group in a Riemann surface, compact. Then there is this problem that really goes back to Riemann, and it asks how many unramified Galois covers can we write for this Riemann surface with Galois group G? Can we just count them? And it's not actually an easy problem, because it's a problem with counting modular automorphisms. So it's really a problem about computing an orbifold Euler characteristic. So if you look at the moduli stack of G Galois covers of flat G bundles on X, you want to compute the Euler characteristic of that stack. That's what this counting problem really is asking for. And in fact, it is a partition function in gauge theory, which is a 2D Dijkgraaf-Witten gauge theory with gauge group G. And there are many interesting variants of this question for higher dimensional manifolds, in particular for 3 manifolds. It's a much more interesting question because higher homotopic groups come in. But for surfaces, what are we doing? We really have a finite set, right? We have finitely many conjugacy classes of representations of the fundamental group of X into G, which is a finite group. But we want to count them in a weighted way. We want to count them taking into account how many symmetries each representation has. So we want the stack quotient of this finite set of homomorphisms by this finite group. So it's a finite stack, finite Deligne-Mumford stack, and we want the orbifold Euler characteristic. And yeah, we know how to do that. For each point, for each conjugacy class of representation, we need to take 1 over the order of the automorphism group of the point and add them up. And of course, because we're dealing with finite sets, it's very easy. This is just the cardinality of the finite set of homomorphisms divided by the cardinality of the group. So we need to count. We need to find this orbifold Euler characteristic. So the interesting thing is this numerator, right? How many homomorphisms do we have, either with up to conjugation or without conjugation? And you can write formulas, but they're not that obvious. So the first formula was written by Frobenius in the case of genus 1. And in the case of a genus 1 curve, the answer is just the number of irreducible representations of G. Right. We are just have a pair of commuting matrices up to conjugation. A pair of commuting elements in the group up to conjugation. And character theory tells you that it's the number of irreducible representations of G. The general formula, I found it in a paper of Mednich from 1978 for the first paper I found, but people tell me that it's actually in the book of Burnside from the 50s, but I couldn't find it there. So this is the formula. It is, again, sum over irreducible representation of the target group. And the fractions you take are the dimension of the representation divided by the order of the group. And the only way the curve appears is through its genus, and it appears because you need to raise this to the power of the Euler characteristic. And maybe Tomasz knows. Do you know where it was written for the first time? Okay. Right. So yeah. So there is another formula with one puncture, which is slightly more interesting, which has an extra term here. And in fact, the way you prove this formula most succinctly is by doing induction on the genus and gluing handles by using the formula with one puncture. Yeah, and so Frobenius actually in the original paper did it for one punctured elliptic curves too. But yeah, anyway. So this is what we're after, right? So we want some formula from of this nature. But now we don't want to take the group to be finite. We want the group to be reductive, and we want to allow for complicated topological data for wild ramification. Okay, so this is what we want. We want Euler characteristic of these guys, and okay, so it will be done. We'll find those formulas, as I said, conjecturally by using some dualities. So there are two stories that are entering in these duality considerations. One is a story that is familiar to everybody here. So if you fix a genus G curve and a rank, so I'm going to do GON now, you look at the character variety, and so this one is kind of unramified, but of odd degree. So you put an extra puncture in a coprime character so that you can get some stability and make it. So you look at projective representations with a prescribed central character to get stable representations and get this character variety to be smooth. So it's an affine scheme. It's non-empty. It has the dimension of the group times 2G minus 2, and it's smooth when this central character is coprime to the rank. And so this is the insight here on the last line that really started all of this, which is Tomasz's insight from many years ago. To say, okay, this is an affine variety. It has a mixed Hodge structure. The mixed Hodge structure carries this, say on the compactly supported cohomology, carries this topological content in it, which is the weight filtration, which remembers something about how this variety can be compactified algebraically. You can, instead of looking at Betti numbers, you can look, or Hodge numbers, you can look at sums of pieces of Hodge numbers, the ones that are only seen by the weight filtration. So what you do is you look at the graded pieces with respect to the weight filtration of the cohomology, and you add them up and you put them in a generating polynomial. So that's the weighted Poincare polynomial of the character variety. And you you can write it, as I said, in terms of Hodge numbers for the mixed Hodge structure, and by duality, you can do it on the cohomology. And then Tamás and Rodriguez Viegas, they came up with a formula for these weighted Poincare polynomials, and they could actually prove the formula by using the Weil conjectures. And then they extended the formula with Letellier for tame ramifications, which I haven't written here, and for wild ramifications, which are of exponential type and with the given Stokes data, given type of Stokes data. But so there is this story where we look at the weighted Poincare polynomials and we arrange them. We combine them with some modified McDonald polynomials, some Cook polynomials, and then we get an actual expression, which looks amazing. Because you see the left-hand side only depends on the genus and the representation theory of the group GLN, and the right-hand side, once you expand it, gives you exactly the weighted Poincare polynomials of all the character varieties. And so we would like to see this formula emerging from some different type of enumerative geometry, and want to see it somehow emerging in full generality for any type of Stokes data. And so that's what I'm trying to explain. And you can try to convert this counting problem of weighted Poincare polynomials of character varieties into something different. And the most natural thing to look at is to look at the non-abelian Hodge correspondence. So you can look at the moduli of Higgs bundles, and then the moduli of Higgs bundles, it's homeomorphic to the moduli of local systems, and then this filtration, which was the weight filtration on the cohomology of the Bethe moduli space, should appear somehow should transform under this homeomorphism to something. And surprisingly, it turns out that it corresponds to a filtration, which is the perverse Leray filtration for the push-forward map with respect to the Hitchin vibration. And so there is this amazing conjecture of Tamás, De Cataldo, and Migliorini, the P equals W conjecture. I don't know if anybody spoke about the P equals W conjecture so far, which says that these two filtrations are matching, that the perverse Leray filtration on the Dolbeau side should correspond to the weight filtration on the Bethe side. And so say in most elementary terms, it says that the vector spaces, the graded pieces of the weight filtration and the graded pieces of the perverse Leray filtration are vector spaces of the same dimension. You can use that. So since we're dealing with numerics, you can use that to rewrite the weighted Poincare polynomial of the Bethe moduli space as the perverse Poincare polynomial of the Dolbeau moduli space. So it's exactly the same thing. And just now you take the graded pieces with respect to the perverse Leray filtration. And that's what we are going to use to translate the problem to a different counting problem, which actually is going to be a counting problem for sheaves on a Calabial trifold. In order to do that, and in the wild case. I mean, this example that I gave was just the unramified case, but you can do it in the temporary ramified case or the wild case. So this second story, which makes the duality possible, it's about knot invariants and algebraic curves. So suppose that you have an affine curve. So plane curve sitting in the affine plane with a singular point, and I'm gonna assume, I mean, in this story in particular, it's always assumed that it's rational. Then you can think about the affine plane as the cotangent bundle of the affine line. You have a projection to A1, and so the singular point projects to some point in the affine line. And your curve will be a finite cover of the affine line if you choose your projection nicely. And you can think about it as the affine part of a spectral curve of a meromorphic Hitchin system on P1 with a Po at infinity. And then you can look at the wild non-abelian Koch correspondence. So the Po at infinity will be of bounded order, and you need to specify the irregular type. But then you can take the irregular Koch correspondence of Bicard and Bouch, and you can identify the symplectic leaf of the moduli of Higgs bundles with this irregular type that contains the compactified Jacobian of this curve, of this spectral curve. So this spectral curve gives you a Hitchin fiber. So you can look at the symplectic leaf containing that Hitchin fiber, and you can identify it with a wild character variety, which I'm now saying depends on the curve because I somehow selected the symplectic leaf by choosing that curve, parametrizing Stokes data at infinity. So the curve already somehow pins down one wild character variety for you. But the curve carries extra information because it has singularity. The link of that singularity is a link in the trisphere because it's a plane curve. And you can write down the Humphrey polynomial invariant for that link. It's a two-parameter polynomial. And there is an expansion in the quantum parameter Q in the Humphrey polynomial, and the leading coefficient in that expansion, I'm calling it P0. So there is some fudge factor that only depends on the Milnor number of the singularity, but then there is once you divide by it, there is some polynomial, and that polynomial in Q it's some invariant of the singularity of that curve sitting inside A2, and then the conjecture of Shende, Truman, and Zaslow is that polynomial is essentially the weighted Poincare polynomial of the character variety evaluated at Q and -1. I mean, there is some topological information, which is the number of branches at the singularity, but that's what the conjecture says. And you can refine that conjecture, so there's some special cases of the conjectures that were proven already by Shende, Truman, and Zaslow, and then you can refine it to cohort extensions, and many cases were studied by Oblomkov, Rasmussen, and Shende, and Diaconescu, and Hua, and Soibelman. And in fact, a very general version of the conjecture was proven by, okay, I now forget, but 4 people, 3 of which are Shende, Truman, and Zaslow. Okay, so the strategy I want to describe is I want to take my counting problem for flat bundles with given irregular type on surfaces and rewrite it as some problem about knot invariance. by using some duality transformations. And in fact, what's going to happen is that in between, there will be another counting problem, which will be a counting problem for Donaldson-Thomas or Poincare-Thomas invariants. Okay, but writing everything in terms of not invariants is actually very good, because the combinatorics, if not invariants are actually computable, and you can get formulas. So you just need to keep track of how you're reformulating your problem and then translate the formulas back. Okay. So as I said, there, aside from the P equals W conjecture, there are three dualities that one is going to use. One is going to use non-abelian Hodge theory and the spectral correspondence, abelianizing the data of the irregular Higgs bundles, to convert the problem to a problem for counting shifts on surfaces or complexes on surfaces. Then that's fairly easy to convert to a problem of counting shifts on Calabial trifolds. And then you use a Gopal-Kumar-Vafa expansion, so that's a physics duality conjecture for this counting invariants for shifts on trifolds, to relate those invariants to something gauge theoretic, which are these refined Chern-Simons invariants. So it's a duality that's called geometric engineering. It's a duality between shift theory on trifolds and gauge theory on a surface, which you can rewrite in terms of not invariants. So these are the three steps, and they lead to formulas in the wild case. So this is the strategy. This clock is correct, right? Okay. Okay, more than 10 minutes.
Yeah, we just started.
A big, okay. So like, okay, good. So to 5 off.
Yeah.
Okay. So these are the steps in the strategy. You start with a twisted wild character variety given by Stokes data and formal monodromies. We want to compute the weighted Poincare polynomial of that. So you use the non-abelian Hodge theory and the P equals W conjecture to get perverse Poincare polynomials of moduli of irregular Higgs bundles. So the interesting part of the story I'm talking about is we want the Stokes type to be not of exponential type. So the terminology that Phil and Yamakawa use is they call this twisted irregular connections or twisted irregular Higgs bundles. Anyway, so these are Stokes data in which you actually need Puiseux gauge transformations, honest Puiseux gauge transformations, not Laurent ones, which complicates the classification quite a bit, and the formulas come out quite a bit more complicated. So we want these guys. We want not irregular connections or irregular Higgs bundles not of exponential type, and then you use the spectral correspondence to convert those as moduli of pure shifts of dimension 1 on a symplectic surface. And so this is actually the main theorem we have, understanding what that symplectic surface is and what that spectral correspondence is for wild Higgs bundles. And once you have this moduli problem for pure shifts of dimension 1 on a symplectic surface, and still you want the perverse Poincare polynomial for those, you do a Gopal-Kumar-Vafa expansion, this geometric engineering, and you rewrite it as a counting problem for refined Poincare-Thomas invariants of complexes of sheaves on a Calabial trifold. The Calabial trifold is going to be very boring. It's just going to be the symplectic surface, which is interesting, cross the line, the affine line. But the sheaf problem on it is not boring. So it's going to consist of sheaves on the Calabial trifold, which will be basically the sheaves that we had on the surface pulled back. And then there will be a map, there will be a section in those sheaves, but the section will vanish also at some isolated points, and those will contribute to the counting. Okay, and then there is this duality with gauge theory, which is called large chain duality, which rewrites this counting problem for refined Pantev-Thomas invariants as refined Chern-Simons invariants of torus nodes. And once you're here, you can write the formulas and then go back.
Surface is the total space of the tangent.
The cotangent bundle, yeah, it will be the total space of the cotangent bundle in the unramified case. Already in the tamely ramified case, it's not the total space of the cotangent bundle. It's a surface that you manufacture outside out of the total space of the tangent bundle. And in the wildly ramified case, it's more complicated. So I'll try to explain. But yeah, it's somehow the starting building block is the cotangent bundle, but you need to modify. And so the tricky part is what happens. You know, it's controlled by the Stokes data, right? What happens when the Stokes data is twisted? How do the modifications work? Okay. So we look at these moduli spaces of flat connections with twisted irregular singularity. And so let me state exactly the problem that we're looking at. So you have, so I'm just going to take one puncture because, I mean, adding more punctures doesn't change anything. It just complicates the formulas. So I'll fix a triple N, L, and R. So I'm looking at connections on a bundle of rank R times L, degree 0, vector bundle on C, and the connection is subject to conditions. So I'm fixing now the irregular types. So there is a stability condition. We have again, you know, like a projective extension, a central character coprime to our bundle at infinity. But at the mark point, we want a pole of order n, and we want the polar part to look like minus 2d times a matrix and then some residue. This irregular type is given, it actually has only two terms. It has a term of degree n minus, power degree n minus 2 and power degree n minus 1. No?
Yeah.
Oh, okay. Okay, so yeah. Right. So this is these are the coefficients, and the residue is going to be block with multiplicities, block diagonal with multiplicities. And so this twisted Stokes data, which is the Betty version of that, that Boauch and Yamakawa constructed, the moduli space of that. It consists of data where, you know, we look at the cyclic cover of the disk of order L. We pull back the irregular type. Then everything diagonalizes on the pullback, and there are two types of anti-Stokes directions. They're okay. So I mean, the names are bizarre, but I think Phil was following the classical terminology. So they're these complete half periods where you prescribe these unipotent groups, and they're just the unipotent radicals of parabolic subgroups with Levy H, where H is the centralizer of our of our picture, and so it's invertible block diagonal matrices. And then there are the incomplete half periods, where you have some unipotent group which is contained in the unipotent radical, but it's smaller. Then you get subgroups of matrices that are centralizing our coefficients. The symmetry group acts by conjugation. The map that inverts these coefficients gives you an isomorphism between the two subgroups, and at the end of the day, you actually get the character variety of Stokes data that is the Bethe version of this Deran problem that I just wrote. It's a collection of matrices. So I wrote them all here. So they're the A's and the B's that we normally have. There is the C at the puncture, which ensures stability and smoothness. There is this H guy that we introduced, and then there are matrices Sj, which belong to the unipotent groups. And you have one relation which says that this is a monodromy representation. This was our condition on the Bethe data. Okay, so this is what you want to study. And Boauce and Yamakawa construct that guy as a symplectic guy by quasi-Hamiltonian reduction for this group-valued moment map quotient by the group GLN cross H. And the value of the moment map should be the formal monodromy. And the formal monodromy in this case is taken to be the generic one, with this block. And okay, so you get a smooth variety, smooth symplectic variety of some very big dimension. So L is, remember, the index of non-exponentiality, the index of twisting, and N is the order of the pole. And R is essentially the rank. I mean, the rank is R times L, but once you unwind, R is essentially the rank. Okay, so we want the weighted Poincare polynomial. It's still expected to satisfy this gap condition that you see for the unramified character varieties. And you know, in small ranks and small genus, you can check that it's true by hand. But in general, I don't know. It's just an assumption that it really happens. Now you can run the program. So you look at the twisted irregular Higgs bundles with the same irregular type. You look at the non-abelian Hodge correspondence, which gives you an identification, a homomorphism between these spaces, and there is a Hitchin map for this wild Higgs bundles, and you assume that the P equals W conjecture holds. And yeah, I actually don't know. Is there a single case in the wild parabolic setting where the P equals W conjecture is known? Oh, just for surfaces, yeah, right. So right, because the Shen and yeah, when the moduli space is a surface, we know P equals W by whatever. Yeah. Okay. Right. So if you fix your Stokes data to be very constrained so that the moduli space is a surface, and we have many examples of those. Well, not many, but they're all enumerated. Then we know. But anyway, so this is really a conjecture here. Okay, so now we do spectral correspondence. As I said, this is the part that's new in this story that's interesting. So we have the classical spectral abilization description by Hitchin and Bhuvil Narasimhan Ramanan, where the spectral curve is embedded in the cotangent bundle, and which is a symplectic surface, and you get pure shifts supported on those spectral curves as the incarnation of the Higgs bundles. So we want the analog of that in the wild case, and it's going to be the same type of thing. It's going to be a modular space of shifts of pure dimension 1 on a symplectic surface. It's just the surface is going to be different. It's going to depend on the Stokes data. And so there are some proposals of how to do that. So Kontsevich and Soibelman did it for GLN and exponential type Stokes data, and we did it in general for other groups and arbitrary Stokes data, non-exponential type. So the way you do it, again, I'm only prescribing the point, the pole at one point. Oh. Yeah, so okay, I'm gonna say this and stop. So you take the curve, you have a surface that you start with, which is the total space of the cotangent bundle of the curve twisted by the polar divisor MP. So that's not symplectic. So it's, it's some birational transformation of the cotangent bundle, but it's not symplectic. And then you start blowing that up. And you have n times L successive blowups at the point which originally starts typically on the zero section over the point P, or it can start at another point depending on the formal monodromy. And you start blowing up, and you get n times L exceptional divisors. And so the blowups, I mean, there is a recipe, right? So there is a untwisting sequence of blowups where we resolve an order tangency between the spectral curve, right? The spectral curve is fixed and it has a singularity, and we're blowing up the singularity of that curve. So you resolve the tangency between the branches of the spectral curve and the exceptional divisors. You need L-1 blowups for that. And then you have another sequence of blowups where you need to resolve the eigenvalues of the untwisted Laurent tail. And then the canonical class of this blown up surface is a combination of a fiber and all those exceptional divisors with multiplicities. But the interesting thing is that the last one enters with multiplicity 0. The last one actually doesn't enter in the canonical class. And so you need to just excise it. You blow up and then you excise this guy. And so you get this picture, and the spectral curves become smooth, and you get this bunch of exceptional divisors. And this is a symplectic surface, and this curve is smooth in it, and you look at the sheaves and follow on the recipe. But okay, I'm not going to show you the formula because it's massive and probably not very illuminating, and I'm really out of time.
Very nice talk, thank you. Is anything known about the topology and geometry of wild character varieties for real groups, in particular related to higher Teichmüller spaces and things like this? What?
I haven't seen anything in that direction. There is a there is a question of how the Stokes data interacts with real forms, and that will be a real, I mean, I don't know how complicated, but it will require serious thought in purely algebraic terms to understand. So the one obstruction to actually doing this, if you want formulas, you really need to work with Stokes matrices and all these ambiguities in the choice of Stokes matrices and the data. And if you want to do computations, you have to do it. But everything depends on a lot of choices. So when you are putting extra conditions like real structures, right, you have to understand how those choices get modified. So there is another approach to this, which is very useful for the geometry, which I didn't mention, where you encode Stokes data in these Deligne-Malgrange Stokes filtrations, which are completely canonical. So you don't need to make choices there. There you quite possibly can see easily what the reality condition does to the Stokes data. I don't think anybody has thought about it. But these Deligne-Malgrange Stokes filtrations, they're about parabolics. It's if you take these Stokes curves of Bouauche, what they are, you put a sheaf of groups. It's not really a sheaf of groups, but it's a constructible sheaf of groups on the surface, where on the open part of the surface outside of the punctures you have just G. On these annulus you have these levies that are given by the Stokes data, and so actually on each sector of the annulus you have the levy. There is some monodromy because of the twisting, and then at each puncture where the two sectors touch, you have to put the intersection of the you put the parabolics of the levies on the sectors, and then you put the intersection of the two parabolics. And so this actually captures the whole Betti picture. These sheaves with structure groups like that, they are the constructible sheaves with structures of group where they are exactly the Stokes local systems. And so you need to take this data and see how it interacts with real structures. So,
thank you. So I just wanted to ask, how about refined Chern-Simons? Could you show us the formulae?
Yeah, I can show you the formula. Somewhere at the end, but it's humongous.
So as far as I know, the refined Chern-Simons is not really defined yet, and possibly for torus knots, but
yeah, but this is only for torus links actually. Yeah, so this, just comes from this Ganagic-Shakirov formulas, the cohort refined Chern-Simons formulas for torus links, and you do get a formula for the weighted Poincare polynomial in terms of, exactly, the same type of polynomials, which, so this is Houzel-Mereb and Wong partition function. And it's expanded in terms of polynomials, and these guys you can actually compute in terms of torus cohort.
But if you vary your Q, can you get any kind of knot at infinity?
Well,
Link.
The links that you get in this picture are by definition algebraic links, right? They cannot be arbitrary. So you cannot get any one of those exotic liquorish links or anything like that. But the question is, can you get non-torus links? Right? That's a question. And I think you can, because singularities of spectral curves, these are like planar curve singularities, which can be pretty much arbitrary. But writing down the Stokes, the irregular type that reproduces the given singularity, it's difficult. That's why you cannot do it for arbitrary irregular types, because I don't know how to convert the irregular type to the singularity. I need to have some control on the coefficients of the polar part of the Higgs field in order to see what the spectral curve is. But in principle, yes, I think any planar curve singularity will correspond to some irregular type that you can write. And so any algebraic knot will appear in this picture. But yeah, that's all I can say.